because it's just, oh, I copy and paste, change some numbers.
As you go, you're watching.
Hi, Jordan.
Right. As distant as it may seem, we did have some homework, which I can't remember what it was. It's last year's solution. Okay, we had a stochastic continuous review model. Does that sound like what we've done? And we were looking for an RQ policy. R is the amount we have installed when we place the following order, well, place an order, and Q is the size of each order. Okay. The Q in that model was we call that the Q comes from the EOQ formula with planned shortages. Okay, so like that. So this one is 2 times demand times cost of one order divided by the stock holding cost, which is the basic EOQ. And for planned shortages, you have to times this by P is the cost of shortages. So P plus H divided by P. That's how you get the Q star. And here I got 60. Well, the first time I tried, I got 21 because I good at it because I divided by 8, obviously. But the right result is 60. And the demand was deemed to have uniform distribution during the lead time. We don't care how long the lead time is. What we care about is what the demand is like as a random variable. And it was deemed to have a uniform distribution between 5 and 15. And remember, you have to have some kind of managerial decision of how many shortages you want or what the probability is that you get a shortage or something like that. So the probability of not having a shortage was set to be 80%. That's the target, so that doesn't come from anywhere. It comes from text of the exercise. And so you want the probability that this demand is less than or equal your R that you're looking for, or R star. You want that to be exactly 80% thereabouts. And so when you do the probabilities, you should get 13. And I got something else in the first time. So that's why there is a second, and that's where I apologize because I forgot to put the spreadsheet in the middle, and I only did so this morning. However, when I had all these wrong numbers here, I went on the spreadsheet, put the numbers in, and gave me a completely different answer. So I corrected it, and
Well, in fact, he definitely knows none of us did this because no one asked him where it was.
okay, so that's what it says here. Correct. And now with this, you want to know what the average number of stock hours per year will be. Okay, so the idea is simple. In every cycle between 2 orders, there's going to be, on average, 0.2 shortages, because you have a 20% probability that there's going to be 1, and an 80% probability that there's going to be 0. So on average, it's going to be 0.2. You just need to work out how many orders you're placing per year. Okay, and the number of orders you're placing per year is, well, every order is 60, and what's the total demand per year? 40 per month, so that's 480 per year. So you're placing 8 orders. Each of them is 0.2, so 1.6 stockouts per year is what you're expecting. Dear viewers, if you can't hear anything, this is because a student is making noise with a pack of M&Ms.
What's it, 2 seconds?
You know, I'm not being serious. I'm never serious. I'm only serious in May when I'm marking the exams, and I get very serious.
How bad they are.
That's 2.
People show it's bonus.
See, I can't even get away with the whole it's anonymous thing because my handwriting is so.
Still not. They don't want to type it.
In fact, you wouldn't even need exams. I mean, there was it's very easy to guess who's going to get it first. So the exam is just a diversion. Of course, in the first year when there's 120 students or whatnot, you can't do it, but modules where there are 10, 15. Most of them, except with the ones who never turn up. With the ones who never turn up, you don't know. Some of them catch up.
Yeah, reads every year. 3 years running.
Yeah. Okay, is that all right?
Mm-hmm.
Anybody got any marks for this? Mary? Yes?
I did the spreadsheet really well.
Did you solve this? Yeah? Okay. So you're on track again to win a prize. Yeah. Okay. What are we doing here? Oh, what are we doing today? We are continuing stochastic models. And in particular, we're doing this one. Which everybody can read on the slide, so I'm not reading from the slide. But the main idea is that instead of doing some kind of continuous review and a long, indefinite, even run of ordering the same thing over and over again, in this case, we're looking at things where you're ordering once, and you have to decide how much. And then during a certain period, you're selling. And if you don't sell, then everything else is lost. Okay, and there might be some salvage price, or there might be even a disposal cost, depending on the situation. Doesn't really matter too much because it's like the same quantity is either positive or negative, whether you're making some money from what's left over at the end, or whether you're having to pay some money for getting rid of it. And this is quite a common situation. I've listed some examples.
What about the third one?
Yes. So when you've got these things, the Christmas trees is not very strictly like this, because when you run out of Christmas trees, the period is long enough so you can order some more. But newspapers and things like that, it is a daily problem, but you can't, if you run out of newspapers, there's no way you can, well, very, very little chance of actually getting some extra ones. And maybe somewhat surprisingly, but quite importantly, these things relate to when you're selling seats on a flight or reservations in a hotel, things like that. Because when you don't, the room for tonight, if you don't sell it by yesterday or today, then there's nothing you can do. So we'll be looking a bit more about, we're looking at flights and pricing flight tickets and things like that next week and the week after. But the basic idea is, well, the basic idea of the whole industry really is here. Of course, just a simple version of it. So as usual, let's do it by means of an example. And the example is this, but whatever it is, it's just an example. That's the example. Okay, you have something, no matter what it is. This case, bicycles. What are the data you need? You need to know how much you're paying for each of the items. You should know how much you can earn by selling one. You should know what the cost or salvage value is if you don't manage to sell them. Yeah. So if you do manage to sell them, you're earning 45. If you don't manage to sell them, you're earning 10. So you're actually losing 10 because you've paid 20 for it. You could be even losing because you have to pay someone to take it away. There's some stock holding costs for things you don't manage to sell as well. In this example, and there could be a shortage cost in the model, where if you run out and people are still turning up, and you have a cost. Stochastic model, so demand will be somehow random, and you typically also know how much you have in the beginning. So the question is how much you should order. Okay. Where are we? Oh, this is a mess. Oh, this is this. Okay. So solving the example goes like this. What are we trying to do? We're trying to maximize profit. Okay. So maximizing profit means we're trying to maximize the following expression. So from each bicycle we sell, we're earning £45. So 45 times the number sold is what we're earning. From each bicycle we don't sell, we're earning £9. Because we're earning 10, but we're paying £1 for storing the bicycle over Christmas, as it says. So £9 times the number of unsold bicycles. And from this, we have to subtract what we paid for all of them. So £20 for each bike we order. So expressing this in terms of two things. S, which is the number ordered. So this is our decision variable, because what we're trying to do is decide how much we order. Okay. And the second variable we have is the demand before Christmas, say. Which is a random variable. Okay, now we're trying to make this fit into the model, which is used. So we need to somehow express it in an odd way. Okay, so I'm going to rewrite the profit in an odd way. So this is going to be 45D minus 45 times maximum of 0 and D minus S. I'll explain in a second. Plus 9 times the maximum of 0 and S minus D. Minus 20S. Okay. Which bit of it makes sense? 20x does make sense, doesn't it? Because that's the number ordered times 20, so that's this bit, so that's okay. How about this?
Makes sense to see that in finance.
Pardon?
It's either 0. If S minus, if D is bigger than S, it's 0.
Yes.
And now, vice versa. S is bigger than D, 0 or not.
Yeah, so the larger of 0 and S minus D is 0 if this is negative, and then S minus D if S minus D is positive. If S minus D is 0, then you have two zeros, so the maximum is 0 as well. Okay. And this is the number of bicycles that are not sold. Because the number of bicycles that are not sold is 0 if the demand is larger than, or at least as large as the number we bought. Okay, so if D is larger or greater than or equal to S, then there's nothing that remains unsold. Okay. But if we had ordered more than we are able to sell, then the difference between what we ordered and what we were able to sell is the number that's left over and so on. So don't go away. Okay? So that's this method. This is a bit trickier. This is expressed like this for a nasty reason. So this is supposed to be 45 times the number sold. So what I'm trying to show is that this will be justified if the number sold is D, take away maximum 0 D minus S. And why is that? Well, so if the demand is less than or equal to S, then this number is D. The demand is at most how much we ordered, then we sell everything, and it's D. And if the demand is greater than S, then the number we sell is S. Because we can't sell more than we ordered. But even if someone just walked in, they would understand that we can't sell more than we ordered. Okay, now check. So if D is less than or equal to S, so this is smaller, so this is negative. So this maximum is 0. So this whole expression is D. That works. And if D is greater than S, then this is positive. So the maximum is D minus S, and D minus D plus S is S. So it works. So in either case, this expression here gives me what I want. All right. So now we're changing the whole thing, because instead of maximizing the profit, 45D is something we can't influence in this formula. So what we're deciding is S, okay? And the demand is a random variable out of our control. So this bit of the profit is independent of what we do. So what we're trying to do is maximize, whoops, maximize this. Maximizing this is the same as minimizing the opposite. So instead, we want to minimize. What do we want to minimize? Well, 45 times max 0 D minus S minus 9 times max 0 S minus D plus 20S. Okay. It's some sort of a cost. So this is clear. This is the cost we pay for buying the bicycles. This is an opportunity cost. Demand turns out to be large. Then we're losing £45 we could make if we ordered more from each bicycle that we would order extra. And this is an obvious £9 cost of negative 9 cost because we have the salvage value of £9 really, and so the cost of not selling them, cost of disposal as it were, is minus 9. Okay. Now in what we're doing, this 45 is going to be called P, which has usually been the shortage cost. This minus 9 is going to be H, which we used to call stock holding cost or inventory cost. And this 20 is going to be C, which is the unit cost. So the exercise of turning that profit into this cost is making more like the other models that we had, where we're trying to minimize cost based on the holding shortage and okay. And Jordan's copying vigorously. Okay. Now it disappeared. You have to trust me. So okay, so what we're trying to do is minimizing now more generally this expression cost based on D, what D is going to be and what S is going to be, and it was P times the maximum of 0 and D minus S, and that's the shortage, plus H times the maximum of 0 and S minus D, so that's the subholding cost, plus the unit cost of ordering these things, so C times what we decide to order, based on a random variable D and a decision variable S. But in fact, that's all nice and great, but the problem is that actually this is not a deterministic expression because there's a random variable D there. Okay, so we can't minimize something that's a random variable. But instead, what we're trying to do is minimize the average or the expected value. So the expectation of this is cost depending on S, okay, decision variable, and that is expectation of C ds over D. Okay, now there's a bit of a problem there. Okay. Just a bit of a problem. Okay, so what's this? What's this expectation of that value? How does this work? Okay, P is a constant, so you need to find the expectation of this. Now, that is 0 much of the time, and it's D minus S the rest of the time. So how do you find the expectation of something? Well, it's a discrete random variable, which in this case it probably is because the number of bikes that we're ordering, or that we're selling rather. So you take the sum of the probability of a value times that value. Okay. Basic probability first here. So you have to sum the value is going to be D minus S, and you times this by the probability that the random variable is this little d. Okay, and you're summing all them. Okay. I should be falling asleep, I'm
I'm falling asleep. I'm
working. Okay, so you take the probability that this is this, and this is going to be the value, but that's only for D's that are larger than S, or at least as large as S. So we're doing this summation from S. Okay. Now the second term is what we're adding H times a sum, and this time this is going to go from 0 to S minus 1. It's the remaining values of D, and there it's S minus D times the probability that this D. Okay. There's a constant with respect to D, so that the expectation of so what do we do with this? Okay, this is okay, so how do you find minimum of this silly thing? Okay, what's your favorite way of finding minimum of functions? That's a bit problematic, isn't it? Because this is okay, that's even more problematic. Okay, this is not quite a linear function in. So you can't use simplex. Differentiation is hard as well because S is only taking on discrete values. So how do you differentiate? Okay, so that's a bit of a problem. However, a good idea. So if we kind of pretend that this is not a discrete random variable, but it's a continuous one, and we know its density, then so the approximate minimum to approximately minimize. I just split an infinitive. I want to write pretend, well, let's say assume that D can be approximated by a continuous random variable. No, that's not continuous.
Continues.
Not easy to speak, write, and be afraid of students at the same time.
Be afraid. And we will not throw them.
Random variable with what's it called? Probability density. The desk is just this. It's just this. I think estate should be worried about their desk shaking. I don't care. It's on my desk. Probability. If it falls apart, I'm not incurring any loss. They are. With is it called probability density? F. Okay, so like
Calling that F.
Was the balance.
I trust you know what I mean, brother. Okay, so like this, what we're doing is minimizing. Okay, I'll rewrite it backwards. Hopefully no one is getting confused. CS, now this sum from 0 to s minus 1, if we're pretending that this is actually continuous, is going to turn into an integral from 0 to, what is it, big S? S minus x. The probability is now fx. Okay. And the second sum is going to turn into an integral from s to infinity, p times x minus s now, times the probability measure. This is an approximate expression for that. And to minimize this, your favorite way of minimizing is differentiating. Now that's a bit okay. So differentiating by s, because s is the decision value. S is there. So this is the derivative of this by s is going to be c. Now this one. That's something you should have done in your analysis, but sorry? Identical. What?
Like if you differentiate something that's got integrals, just get rid of it.
Yeah.
That one's done.
But it's not so simple. Okay, I'll rearrange this. What do I do? So this bit here, I'll call it, give me a letter, A. Okay, A of S, because it's a function of S. So if I want to differentiate this by S, what happens is I need to split it through this. A of S actually is different into integrals. So first I want to do d by ds of 0 to s s times fx dx. Okay, and the second part is, oops, not plus, but minus rather, integral 0 to s x fx dx. Okay. So far, so good. Now, okay, with respect to the integral s, this s is a constant. So I can actually write it out of the integral. So this goes away. It goes here. Sorry. I need to rewrite it all. Okay. Now the question is, no, well, the answer is, Colin knows it. You just get rid of the integral. Okay, so if you're differentiating by x, this means, you're differentiating by s, an expression where this s is only the bound of the integral. And this is going to be the function inside in S. Yes.
What have you done to you?
Yeah, that's what it says. Okay.
I'll be back on the show.
Okay, so this is going to be minus S f of S. Yeah.
Wait, you mean you just substituted S in?
Yeah, but this is how, yeah, so you just get rid of the integral. It really is like that. Because so integral and derivative are in some sense inverses of each other.
What are the inverses of each other?
Boundaries then doesn't equal
Well,
X is 0, which makes it
yes,
zero
but in
anyway.
a very specific sense. They're not like inverses.
Are you declaring that that is the same as SFX?
So
It's the
d
second
by
term.
ds of this term is SFS.
That whole thing?
No, just this.
This
Just that bit.
This bit. So this bit you have to do because it's a product of two functions.
Oh, something 0, X 0, which makes the term 0 doesn't it? On the second part of it. Yeah.
Okay, so this is so this
Yeah.
you know, like, but it doesn't matter that if you put in 0, X 0. It doesn't matter where you start. If you start minus 2, but it's the same result.
And that's probably
So it's kind of like when you think of, okay, what is the converse of the derivative? Sometimes so it's always good to think of some kind of a physical interpretation. For example, if you have a position of something, the derivative of the position is the integral of the speed is the position. So if this is the speed in point X, we're looking at how far it travels if you let it go from 0 to S with this speed. I'm from 0 to S, dealing with this speed. So this integral is going to tell you how far the ball has traveled. Now, if you're differentiating it by how long you let it travel, it's going to get is again the speed. So that's the first. So the second bit is easier. The first bit you have to do is the derivative of the product of two things, which is not much harder. But okay, so if you're differentiating S turns into 1, but what you're left with is the integral from 0 to S x dx. And then the other one, you leave S alone, but you differentiate that, and what you're going to get is f of S. That they cancel.
Explain that first part to me again, yeah. The integral of 0 to S fx dx, and then it's the plus sfs.
Okay. So this
I know where you got that from. That one's perfectly explained.
Okay.
It's those ones.
What you're differentiating is S times this integral.
Right.
When you're differentiating the product of two functions, it works. The derivative of the first one times the second one, plus the first one times the derivative of the second one.
Yeah.
So here, derivative of s is 1. Times the second one.
Yeah.
Plus the first one times the derivative of the second one, and the derivative of the second one is by the same version here, f of s.
Right.
Right, so, and the time runs out.
Don't care. 2 more minutes.
Yeah, but it needs more than 2 more minutes. Okay, so in fact, what you get is okay. So I promise. C, okay, which is coming from that first term, C times S. The second we've just seen is h times the integral from 0 to s f of x dx.
Bonuses.
This doesn't make sense. Oh, right. And the second one, I don't believe. You get something like minus h times some integral f of x dx, but I don't know. I don't quite trust my notes. So, there's a homework, is there? Does it need the result
Can't
of
even get
this?
the pages separated. Good job, mate. There we go. Yes, there is.
Okay, so, which means that we can't solve the homework. Homework is to look at this in the books and see how you differentiate the second bit and see whether this is correct or not. And we'll see this next week. Yes, I'm going to finish this next week. And then we'll move on to all those plane tickets. Okay? Any questions? All good?
Well, just a statement really. It's official. You've officially made OR boring now. It's the rules. I hate them. Well, single.
That's
They
not
don't
boring,
need it,
that's
yeah.
just tedious.
Yeah, exactly. I went in to see Leader. And like,
Okay, I'll stop the
came out,
broadcast now.